So this talk is based on some joint works together with Ben Green and Farouk Labib, and it's about things called dual functions. So let me jump right in and try and explain to you what a dual function is. I'm allowed to switch. Yeah, okay. So there's some basic examples called arithmetic progression dual functions. These are special cases of the more general ones I'll be considering. But let's start with this. So a three-term arithmetic progression dual function is a function taking values in the complex unit disk, I'll denote by D, and its domain for the purpose of this talk will just be a finite abelian group. And you should always think of this thing as either a cyclic group, so Z mod n, or a vector space over a finite field, Fp to the n. And so a dual function is a function of a particular form, shown here. It depends for its definition on a triple of other functions, f, g, and h, and it's given by the average of the product of f and g and h, where you evaluate this triple of functions on the points of a three-term arithmetic progression. Okay, and so the average is taken over the starting point of the progression, and the value of the dual function is given by the common difference d of the progression. So an example of a 3AP dual function is one that's given by the indicators of some subset of your group. So A is a subset, FGH are just the indicators, the indicator of this subset. Then the corresponding dual function evaluated at some common difference d will simply give a count of the number of 3APs in your set whose common difference is d. So if you average over d, then what you get is simply the proportion of 3APs in your set. So as you can imagine, dual functions play an important role in questions in additive combinatorics, and especially when it comes to counting linear patterns. So like I said, this is a special case of the type of dual functions I'll consider. The more general ones are given in terms of more general patterns than 3APs. So here's the definition. An order k dual function is given in terms of, first of all, a pattern. So that's a length k integer vector, and k functions, f1 up to fk. And it's given again in terms of the average of a product of these functions, where you now consider, instead of a three-term arithmetic progression, a linear pattern of length k, where the coefficients of the common difference, if you will, are given by the coefficients of this integer vector I. So the 3AP dual functions are special cases of these order k dual functions, where the pattern is given by the integer vector 0, 1, 2. Okay, so these are the most general types of dual functions I'll be considering in this talk. And now I realize that maybe the word dual functions could be confusing, because this term is also applied to functions associated to the so-called Gowers uniformity norms. I expect many of you know what these things are, but if you don't worry. For a function, it's Gowers K uniformity norm can be given in terms of the inner product of this function with a version of this function that I'll denote by dk of f. And this version of this function is given as follows, kind of a complicated expression. So I'm not going to read it out literally, but roughly speaking, it's the average of the product of the function with itself evaluated on the points of a k-dimensional parallelepiped with the origin removed, if you will. And these C's just denote complex conjugates that you have to take here and there. Okay, so this is one way you can write out the Gowers K uniformity norm of a function f. What I wanted to mention with regard to dual functions is that the version of this function f, denoted dk of f, are also sometimes called dual functions. And in this case, it's very reasonable that they be called dual functions, because you can define the Gowers K uniformity norm in terms of these types of functions. The dual of the Gowers K uniformity norm is given in terms of these types of functions. So maybe I should call these Gowers dual functions, and I'm not sure what to call the functions I defined before, but they are also called dual functions. And there's a relationship between them, which is that the Gowers dual functions, they lie in the convex hull of order K dual functions for some pattern of length K. So not necessarily, to the best of my knowledge, not necessarily K-term arithmetic progression dual functions, but dual functions based on some other pattern. I think that pattern may actually depend on the group G here. Anyway, so there is a relation between these types of dual functions, and it's the order K dual functions for some patterns that I'll be most interested in this talk. And the thing that I'm interested in this talk for these functions is decompositions. I would like to understand how you can write dual functions in terms of more simple functions. So decomposition functions is the main theme of this talk. And there's a very nice example where you have very nice decomposition, and that's the example of order 2 dual functions. So an order 2 dual function is just given in terms of two integers, I1 and I2, and it's given in terms of this average for functions f and g that define the dual function phi. So this is just an order 2 dual function, arbitrary one. And you can write this thing very nicely in terms of the characters of the group. So the chi's here are characters of the group G. So far, there should be nothing surprising here because the characters form a basis. And so these coefficients in this decomposition are just the Fourier coefficients of the function phi. So any function can be written in this form. But because this is an order 2 dual function, it has a very specific form that implies that the Fourier transform obeys something that's not typical at all for a general function, namely that its lowercase l1 norm is at most 1. So this is just the sum of the absolute values of the coefficients alpha chi here. So you can show this. It follows essentially because the expression here can be thought of as a convolution, and so the Fourier transform, or the Fourier coefficients, are the pointwise product of the Fourier transforms of f and g. And then you can apply Cauchy-Schwarz and the fact that f and g are assumed to be bounded by 1 in the definition of an order 2 dual function. Okay, so in a sense, order 2 dual functions can be written as convex combinations of characters. And this is a type of decomposition that I think is optimal in many senses. It doesn't get much better than this. Unfortunately, you don't have decompositions like this already for order 3 dual functions. So here's a bad example that shows that you can't do something like this for order 3 dual functions. I'm sure it'll look familiar to many of you. So if we take for the group vector space over F3, and we define 3 functions as F, G, and H as these quadratic functions where omega is now a complex cube root of unity. Then if you evaluate the product of these 3 functions evaluated on the consecutive terms of a 3-term arithmetic progression in direction D, then what you find is that this product only depends on D and not on the starting point X, and it's given by this simple quadratic function here. And now if you consider the dual function based on this triple f, g, and h, which means that you have to average over x. That average does nothing because this thing does not depend on x. Then what you find is that the Fourier coefficients, the alpha that you see here, they don't have bounded L1 norm. Their L1 norm is actually exponentially large in n. So you can show this using basic Gauss sum estimates if you like. So unfortunately, order 3 dual functions can't be decomposed in such a nice way in terms of characters. However, there's something you can do if you are willing to move away from decompositions in terms of characters. And you can do this using so-called inverse theorems for the Gowers uniformity norms. They allow you to approximately get decompositions for higher order dual functions, so dual functions of order higher than 2. These inverse theorems, there's various versions depending on the types of groups you're working over. They roughly say the following. I hope you'll forgive me for being somewhat imprecise. If your function has a large Gowers UK norm, then there is some other function, psi, that correlates with your function, has large inner product, where this psi has a very specific form. If you're working over finite cyclic group, then this pi is something called a k-1 step nil sequence, actually one that has bounded complexity as well. I'm not going to go into the details of what these nil sequences are. It won't be so important for the rest of the talk. If your group is a finite vector space whose characteristic is at least k, then this psi can be taken to be something called a polynomial phase function. So that's the function of the form omega to the p of x, where omega is a lowercase pth root of unity. And p is an n-variate polynomial over f of p, whose degree is at most k-1. Perhaps a simple example of a nil sequence is a function of this form where p is a univariate polynomial over z mod n. So this is a rough form of these inverse theorems for these two different groups. There's also one where you assume the characteristic is lower, but it won't play a role in this talk. So we'll refer to the functions that you see here, nil sequences and polynomial phases, as order k characters. So in this picture, the usual characters are the order 2 characters. And there's a basic technique that I think is due to Gowers, where you combine these inverse theorems with the Hahn-Banach theorem and something called the generalized von Neumann theorem that allow you to express higher order dual functions in terms of these higher order characters. So combining these ingredients, what you can show is that for any k and epsilon of your choice, an order k dual function for any pattern can be written as a linear sum of order k characters, where the coefficients that you multiply these characters with have bounded L1 norm, and where there's a small, you have to add a small error function, and this error function is small on average. So the uppercase L1 norm of this error function is epsilon. Average absolute value of this error function tau is at most epsilon. Okay, so this is a very nice decomposition theorem that holds in general. So let me just contrast this with the example we saw before. Order 2 dual functions allow for a decomposition like this. You can write them as sums of order 2 characters or just normal characters, where the coefficients have L1 norm at most 1, and where this where the error function is actually 0. For 3 AP dual functions, that gave a counterexample on the previous slide. So 3 AP dual functions always have this form. You have a triplet of functions FGH, taking values in the complex unit disk. You can always decompose them as a sum of polynomial phase functions of degree at most 2, where the coefficients have a 1 norm that's bounded, and where this error function is bounded on average. So these are really nice decomposition types results, and they have applications in additive combinatorics when it comes to studying linear patterns in dense subsets of groups. But they also have these kind of decomposition theorems also have their limitations. And the reason for that is that there's actually quite little control over this error function. So this error function is small on average, but there are some applications in additive combinatorics where ideally you would like to have an error function that's small everywhere. So the main question you can ask about these decompositions is if there's a similar decomposition where indeed this error function has bounded L infinity norm. So it's bounded everywhere instead of just on average. So the abstract and the title of my talk already gave it away, and I'm just going to give it away again. If you prefer to stay in suspense, please cover your eyes and ears. It turns out that this is impossible, and that's what I'm moving towards in this talk. But before getting into the details, let me just spend a bit of time on motivation. So why should you care about these kinds of decompositions? That has to do with certain special versions of Szemerédi's theorem based on things called intersective sets. Let's say that a subset of the integers between 1 and n is S intersective if any dense set contains an S plus 1 term arithmetic progression whose common difference lies in this intersective set. So there's some very nice examples of intersective sets that hold for every S. First of all, Szemerédi's theorem shows that n itself is S intersective for every S, provided n is large enough. The squares also are S intersective for every S. This is a special case of a general result by Bergelsen and Leibman. The shifted primes are also S intersective for every S, the general result of Woolley and Ziegler. Perhaps I should say that there was previous work on these last two results that consider the case where S is equal to 1, I believe by Sarkozy, and apologize, I forget who else worked on these things. The integer parts of fractional powers of the integers are also intersective. So there's lots of nice examples. And based on these examples, in particular, Franzikanakis, Lessange, and Weerdle asked the question if these sets are special or if random sparse sets are also typically intersective. So to make this slightly more precise, the question or the problem that's often referred to as Szemerédi's theorem with random differences asks, what's the smallest number, rho S, for which a Bernoulli rho S random set of your group is typically S intersective. So here I'm letting the group be an arbitrary finite abelian group again. A Bernoulli rho S random set is one that contains every element of your group independently of the others with probability rho S. And typically here I'm taking, I'm interpreting as holding with probability, say a half. A half is arbitrary. I'm happy with just positive probability. So we know very little about this problem. There's some upper bounds. Rho 1 is at most log n over n. So a typical set of size log n has the property that any dense set contains a pair whose difference lies in this set. You can show this actually using the fact that order 2 dual functions can be efficiently decomposed in terms of the characters, where efficiently I mean that the coefficients have L1 norm at most 1. Rho 2 is bounded from above by roughly 1 over root n. This is a result independently proved by Christ and Franzikanakis, Lessange, and Weerdle. And somewhat oddly or ominously, the same bound holds for rho 3. And this pattern persists for larger subscripts, making jumps over the uneven numbers. We always get twice the same bound and then a jump at the next uneven number. So this rho 2 bound is likely not optimal. And I expect the rho 3 bound not to be optimal either, actually. As far as lower bounds concerned, it was shown by Franzikanakis, Lessange, and Weerdle that for every S over this cyclic group of size S, rho S is at least log n over n. Over finite fields, Altman somewhat surprisingly showed that there the situation is somewhat different. So rho 2 is at least n squared over the size of the group. So you can interpret this as kind of a square of the logarithm of the size of the group compared to the cyclic setting. And this result generalizes for larger S. Okay, so these upper bounds and lower bounds are very far apart from each other. In fact, the lower bounds are conjectured to be optimal. So the conjectures appear to be that the upper bounds are very far from the truth. This is a conjecture by Franzikanakis, Lessange, and Weerdle over a cyclic group size n. Rho of S is at most log n over n for every S. Constant maybe depending on S. The main motivation for this conjecture appears to be the expectation that order k dual functions can be decomposed, roughly speaking, as convex combinations of order k characters plus an error that's bounded everywhere, bounded in L infinity norm. Okay, so we don't know this to be true. So I'm saying this is an assumption. I think so. This statement here falls just short of some conjectures that have been posed in the literature. These conjectures allow either for things called generalized nil sequences in the integer setting, or they restrict dual functions to be non-negative functions and always based on the same. Instead of three different functions, say FGH, they have to be the same. So I can't quite attribute this statement to a formally posed conjecture, but it appears to be that the expectation is that this should hold. If this holds, also the lower bounds in the finite field case would actually be optimal. This is not something that's been formally conjectured, but it seems to be that this was the expectation. Okay, so finally moving to the main results of this talk, the main results say that this assumption is false in general. First of all, I want to mention a finite version of a recent result with Ben Green. The finite version of this result says that the set of three AP dual functions over Z mod n can't be approximated in L infinity distance by, let's say, convex combinations of two-step nil sequences. The actual result is posed in an ergodic theoretic language, which is more or less an infinite setting. And I don't really want to go into that in this talk. So I try to keep things somewhat elementary here. The second result says essentially that things go wrong in the finite field setting as well, but it's not quite as clean. So here we get counterexamples to the idea that order k dual functions can be approximated by degree k minus 1 polynomial phases. But here, the counterexamples, so the k's depend on the characteristic of the field we're working over. And also the patterns of these order k dual functions we have little control over. So we don't currently have a statement like this talking, for example, about three AP dual functions over F3 to the n. Okay, so I see roughly halfway and I've finally gotten to our results. For the remainder of this talk, I'd like to say a little bit about what goes into these results, how you prove them. I'm going to start with the integer setting. The proof sketch is as follows. It relies on what we'll call a key lemma. The key lemma asserts that there's a subset D, should be interpreted as a set of maybe common differences of size omega log n, such that the projection of the three AP dual functions on this set D approximately contains a full dimensional Boolean hypercube. So by approximately contains, I mean that this hypercube might be slightly scaled down and slightly shifted, but only by constant factors. Okay, so this is the first ingredient in constructing the counterexamples. The second ingredient is a fact that follows, I think, from results of Frantziki-Nakis, which says that because the set D is so large, omega log n, you can find a delta net in L infinity distance for the set of two-step nil sequences on the integers mod n, whose size is 2 to the little o of d, so very small size, definitely small compared to the size of this hypercube here, and that's the main point, where delta goes to 0 as n goes to infinity. Okay, so these are the two facts one can use together to prove the counterexamples. And to put these together, I'm going to use a measure of, let's say, complexity. And that measure is called the width, or Rademacher width. It's defined as follows. For a compact set in C to the n, you define its width essentially as the average maximal inner product of a point in your set and a randomly distributed -1,1 vector. So a point in the n-dimensional Boolean hypercube. This width roughly measures the average width of your set in a randomly chosen direction. So here, theta should be interpreted as a direction, say. So this width has a number of very nice properties. It's monotone under set inclusion. It's subadditive under some sets. Taking convex hulls does nothing to it. And the width of the n-dimensional Boolean hypercube, let's call it its complex analog, is equal to n. Okay, so how do you put these things together to get counterexamples? Let me just remind you of what we're aiming for here. So suppose what we'd like to do is decompose a 3AP dual function as a sum of two-step nil sequences where the L1 norm of the coefficients is bounded by some L, and the L infinity norm of the error function is also bounded. Okay, so this is what we'd like. And let's assume this is the case. And what we're going to aim for is show that this number L can't be constant. So another way to phrase this assumption is that the set of 3AP duals, that's the size, lies in the convex hull of an L scaling of the two-step nil sequences, that's this first term here, plus an epsilon scaling of the complex hypercube. So this is the assumption we're starting with. Well, then the key lemma said that the 3AP duals contain a high-dimensional hypercube after projection to this set D here. That's the first key lemma. And then this result of Franz-Sikinakis told us that we can very efficiently cover the set of two-step nil sequences by a finite, smallish finite set with very small L infinity error. Okay, so this is the picture we're going to be using. And now we're going to use this width I've just defined. First of all, like I said, it's not difficult to check this. I'm not going to prove it, but it's not difficult to convince yourself of. The Rademacher width of the Boolean hypercube of dimension cardinality of D is the cardinality of D. The second property of this width that I'm going to use is that it's monotone under set inclusion. And the set inclusion I'm going to use is that this blue hypercube is contained in this outer pink set. So I'm going to ignore the other sets. And this pink set is this convex hull plus a scaling of the complex hypercube. Okay. Okay. So the width of this d-dimensional hypercube is at most the width of this complicated looking set. I'm going to simplify this latter expression now. The width is subadditive under some sets. So what you see here is the sum set of this convex hull and this scaling. So I'm going to use subadditivity now to break these two things apart. The width is also unchanged under taking convex hulls, so I can remove this convex hull. And then what I left here is another sum set, so I can break this thing apart again. And now I'm going to start using the basic bounds for the width. First of all, I have the width of an epsilon scaling of this d-dimensional complex hypercube. That's exactly epsilon times cardinality of D. Similarly, what I have here is L times delta times the width of this hypercube. Now, delta was a number that went to 0, so you can bound this width from above by L times little o d. I know the last width to deal with is maybe the most complicated, but there's nice tools that allow you to bound it. What you have here is a scaling of a finite set. So C here was a delta net for the set of two-step nil sequences. So you have a scaling of a finite set of one bounded functions that are defined on a set of size cardinality of D. It turns out something called the Khinchin inequality then tells you that this width is bounded from above by this scaling L times the cardinality of D times log of the cardinality of this delta net. So this delta net had size 2 to the little o cardinality of D. And so what you have in the root here is also little o of D. So it's comparable to this second term here. Okay, and now you're basically done when it comes to proving a lower bound on this L. If you rearrange this and you use that D goes to infinity, what you find is that L is not bounded. So that means that if you have a 3 AP dual function and you want to write it with this kind of decomposition where the psi's are two-step nilsequences, alpha has L1 norm at most L and tau is L infinity of most epsilon, then in general, this L cannot be bounded. There will be a dual function for which this L won't be bounded by a constant. Okay? So that's kind of the high level overview of what goes into showing counterexamples for efficient decomposition of 3 AP dual functions in terms of two-step nilsequences. What I'd like to go into next is this key lemma that said that 3 AP dual functions contain high-dimensional hypercubes after projections. So this is the key lemma. Projection of the 3 AP duals contains, roughly speaking, a full-dimensional hypercube. So the ideas behind this key lemma come from coding theory, and in particular, a basic construction of a more complicated result of Vichanen that I'll mention later in the finite field setting. So the construction of this high-dimensional hypercube starts with a very basic observation. If you take any pair of two-element subsets of a set of size n, and you look at the inner product between the indicator of the first and the indicator of the complement of the second, and this inner product is 0 if the sets are equal, and it's 1 or 2 otherwise, because this first indicator only has 2 non-zero coordinates. Okay? It's a very basic observation. And now you combine this with the following thing. Let gamma be a non-zero element of F4. That's a root of the polynomial 1 plus lambda squared, polynomial over F2. Well, then if you evaluate this polynomial on the point gamma to the inner product that we discussed just now, then this polynomial evaluates to 1 if the sets S and T are equal, because then this inner product is 0, and what you have here then is 3, and 3 is equal to 1 mod 2. And otherwise it's 0, because this polynomial evaluates the 0 of on gamma, of course, which you get if the inner product happens to be 1, but it also evaluates the 0 on gamma squared. I think this fact is sometimes referred to as the freshman's dream, because we're working over F2 here. Okay, so based on this, we can now start moving towards defining functions that will in the end give us 3 AP dual functions that contain high-dimensional hypercubes. So the goal is to construct high-dimensional hypercubes, and associated to each point of this hypercube will be a Boolean vector, A, indexed by the two-element subsets of n. So those are the S and the T's here. To get real valued functions, we'll need a character. In particular, we're going to be using some additive character of F4 that we'll choose later. And the functions that we're going to use to define the 3 AP duals are going to be built out of functions of this form. They take integer vectors to -1, 1, by sending a point to the evaluation of this character on this big sum here. Okay, so I'm not going to read it out. Most important thing is that the coefficients, they come from this Boolean vector A. So for every A, I'm going to define a function F. So in total, there's going to be roughly n squared functions f. These functions have an extremely nice property, which is that if you look at their product with themselves evaluated at 3-term arithmetic progressions, whose direction is the indicator of a 2-element subset S, well, then this product can be simplified by using the fact that we're using additive characters here. So you can take the 3 sums that you appear inside of a single additive character. And then you use this property, the third property I listed here, to show that the big sum you're left with collapses to a single term that depends only on the direction you've chosen here. So this direction is just some given in terms of a 2-element subset. Okay. So if the coefficient of the subset you chose to take the direction in happens to be 0, then this character evaluates to 1. And ideally, what you would like is that if this coefficient is 1, then you get -1. If that's the case, then actually for every choice of A, you would get another point in the roughly n squared dimensional Boolean hypercube. That's not quite the case because you have this extra term that depends on the starting point of your 3AP x. So to deal with that, you're now going to define the character. You choose the character such that at least on average over x, you get something that's non-positive, okay? And the average here is taken over a bit of a funky set that will become clear in a moment. So the average is taken over all the integer vectors whose coordinates take values between 0 and n-3. Okay. So now we're pretty well on our way to finding high-dimensional hypercubes. What we have up to now are functions f that have this property. If you take this average over x with coordinates between 0 and n-3, then the product of this function along a direction given by any 2-element subset is 1 if the coefficient of the Boolean vector that defined the function is 0, and it's non-positive otherwise. So it's starting to look like a point in the Boolean hypercube if we realize that this set A was arbitrary. Okay? We're not quite there yet because we're aiming towards defining functions over the integers mod n. And these we're averaging here over integer vectors and not points in Z mod n. So to deal with that, we're going to apply a basic trick. We'll let capital N be lowercase n raised to the lowercase n, and we'll let beta be the standard base n representation map. So the map that sends every element in 0 to n-1 to its base lowercase n representation. We're almost there. Then I'm going to take 2 sets. The first set should look familiar. It's a set of points in Z mod n whose vector under beta has coordinates in 0 to n-3. Okay, so that's exactly the set that we're averaging over up here. And the most important thing about this set is that it's dense in n. Okay? And the second set is simply a set of elements in Z mod n whose coordinates base n are Boolean. And these 2 sets have the property that the map beta, the base n representation map, is roughly speaking linear when you take linear combinations of the form x and a, y and b, and the coefficient of y is 1 or 2. Okay, so the only reason this works is because there's no carries. So this a kind of caps the coordinates of the vector x, and I times y doesn't go over n-1 in a sense. Okay, so now we're basically done. We can define now a direction in Z mod n to be the inverse image of a 2-element subset S under beta. And then we can define a triplet of functions based on which you get a 3-term arithmetic progression dual function. And these functions are essentially given by the composition of f and this map beta. So here you use the fact to, okay, so to get to this conclusion, use the fact that beta is essentially linear. But for it to be essentially linear, you need x to be restricted to this set A. And to do that, you pre-multiply the first function by the indicator of this set A. So this doesn't do too much because A is dense. And so for that reason, you get to that these expectations, they're not exactly plus or minus one valued, but if the AS coefficient is 0, then you get some constant. This constant is exactly the density of the set A, and otherwise you get something that's non-positive. The point here is that for every choice of Boolean vector A, there was a function f that gave you a dual function with these kinds of values. And this is what I mean when I say that the set of 3 AP dual functions contains approximately a high dimensional hypercube. So this is kind of the outline of the construction in the integer case. In the finite field case, the ideas are very similar. So let me just remind you of the statement here. So for infinitely many primes, there is some k and a set of order k dual functions that cannot be approximated in L infinity distance by polynomial phases of degree at most k minus 1. So here's another key lemma that goes into proving this. That's very similar to the lemma I stated before. So now you have some subset of fp to the n, whose size is very large. So it's 2 to the little omega of n to the k minus 1, such that the projection of order k dual functions of a certain pattern to this set contains essentially a full dimensional hypercube. And you can combine this with a somewhat easy fact that the number of polynomial phases of degree k minus 1 is asymptotically smaller than the size of this hypercube here. Okay? So I'm not going to go through this again, but the idea is similar here. Instead of having an efficient delta net, we don't even need that here. There's just too few polynomial phases to approximate every point in this hypercube. I would like to say a little bit about what goes into the key lemma here, and that relies on a pretty surprising result of Vihanens that says the following. P and Q are distinct primes, and T is the multiplicative order of Q mod P. Then there are omega into the T orthogonal pairs, which are sometimes also referred to as matching vectors, ui, vi. By orthogonal, I mean that the inner product between ui and vi is 0, such that the crosswise inner product, so the inner product between ui and vj, when I is not equal to j, is a power of q. I'm not going to go into the construction. It's not super complicated, but it is quite clever. And it, roughly speaking, uses something akin to a tensor power trick, where the basis vectors are the ones that I sketched before in the integer setting. Okay, so how do you use this to construct high dimensional hypercube? Before we had some very simple polynomial, 1 plus lambda squared. Now we have some other polynomial that we have to find to suit the construction. So suppose P is some polynomial over FQ that evaluates to 1 on 1. And suppose that it has a root gamma of order P and supports at most T. So there's at most T coefficients that are non-zero in this polynomial. Well, then you can use the properties of these matching vectors to convince yourself of the fact that when you evaluate this polynomial on the point gamma raised to the power inner product between ui and vj, I should say that this expression makes sense because we assume that gamma has order p, and ui and vi come from fp to the n. This expression is 1 if I is equal to j, because p vanishes on gamma, but also any qth power of gamma, again, because of the freshman stream, and it's 0 otherwise. Sorry, I misspoke. So clearly it's 1 if I is equal to j, because the inner product is 0 then, and it's supposed to evaluate to 1, and otherwise it evaluates to 0. Based on this, you can now define a number of functions based on which you get dual functions. So here the indices L, they correspond to the indices of the monomials in the polynomial P. So we have some binary vector A and a character that you choose again later. And for every L, you define a d-valued function on fp to the n, somewhat similarly as we did before, except now you include the coefficient, the Lth coefficient of this polynomial. Okay. These functions have the property that if you multiply them, but only those that correspond to indices in the support of the polynomial, and you evaluate them on patterns in direction ui, where the coefficients correspond to the non-zero monomials of the polynomial. So this tuple here defines some pattern that depends on the polynomial p. Then this big sum again collapses to a single term. That's obviously 1 if the coefficient of this binary vector in direction I is 1, and it's well, you can make sure by choosing chi judiciously that it's non-positive otherwise. Okay. Okay, so now, excuse me. To get examples, so high-dimensional hypercubes, what you need is a polynomial that's t-sparse, so it has at most t non-zero coefficients. If you have that, then you get patterns whose length is smaller than the dimension of the hypercube you get from this construction. So to make everything fit, you now have to find polynomials that suit the construction. But it turns out that indeed over F2, you get t-sparse polynomial when the order of 2 mod p is strictly less than p minus 1, and it turns out there's infinitely many of these. I think this follows from a result of Chibotara, but there may be other results that imply this as well. And there's also extreme examples of polynomials that are 3-sparse if p is a Mersenne prime. So these give you, in a sense, extremely strong counterexamples to the desired decompositions. Okay, so these are a fair number of the details, I suppose, of the counterexamples. I'd like to devote one word to where these things come from. So these examples come from an area of coding theory. In particular, they come from constructions of so-called locally decodable codes. So this result of Yechanan's I just quoted has to do with extremely good constructions of locally decodable codes. So what a locally decodable code does is it encodes a message, say an m-bit binary string, into a typically longer code word that in this setting you can think of as a function that maps a finite abelian group to -1, 1. So in this case, the coordinates of the code word are indexed by the elements of your group. And a locally decodable code has the property that any single index of the message or any single coordinate can be retrieved from the code word by only looking at a very small number of code word coordinates, even if the code word is partially corrupted. And now the link with AP dual functions is that the constructions I gave you of the AP dual functions are locally decodable codes. And roughly speaking, you can see that because the coordinates that are sampled to retrieve a single message bit, they correspond to the patterns. For example, a 3-term arithmetic progression pattern is sampled randomly among the triples of code word coordinates. And from them, you could retrieve a single message bit. And the reason why this works, even when a constant fraction of the code word is corrupted, is because each individual coordinate of a 3AP is uniformly distributed. And so by a union bound, you're quite likely to avoid the corrupted part of a code word. Okay, so this is kind of the origin of these counterexamples. To finish up, I'd like to mention a few open problems. The first is that we don't have counterexamples to good decompositions of 3 AP dual functions over f3 to the n. So our constructions unfortunately give us no control over the length of the patterns and also not of their nature. So we don't get AP dual functions of any form using this construction, actually. The second has to do with Gowers dual functions. It's to the best of my knowledge, I don't think these counterexamples imply that the Gowers dual functions can't be decomposed in terms of higher order characters with small L infinity error. These examples also don't say anything about Szemerédi's theorem with random differences. All they seem to do is kind of block a proposed line of attack to prove optimal bounds for Szemerédi's theorem with random differences. So this stays completely open. And finally, I think this is interesting mostly from the perspective of coding theory, is if there are worse examples. So examples that show you for example, 3 AP dual functions contain even larger Boolean hypercubes than the ones I showed you already. And so there's a lot of freedom in answering this question in a good way. You can stick with the groups I've mentioned. You can also consider what happens when you go to other groups. Maybe non-abelian groups give you even worse examples. And that concludes what I wanted to say. Thank you very much.